Let's say I were to give you this function here. Y is equal to x squared minus 2x minus 5. And I were to say, okay, why don't you find the roots of this function? You'd say, okay, no problem. I can do that. I could try to factor that, although I don't know if that would work. But no need to fear. I also have completing the square. I could use the quadratic formula. I have all of these tools in order to find the roots of this function. And that's a majority of what we've spent the previous math classes getting tools for. But now, let's say this. I were to give you another function. I were to give you this function. Y is equal to x cubed minus 2x plus 1. And we're to ask you, okay, why don't you now find the roots of this function? You would say, that's a tricky one. I don't know. And you don't have the tools in order to, we don't have the tools to find the roots of this function yet. And probably the best that you could do is try to graph this out and try to guess at what the roots are. So let's first get a graphical understanding of what this looks like. I graphed this out on Desmos just to give you a feel for what this function here looks like. Again, we'll let y be equal to f of x. We will call this function. And you can see this function here has 3 roots. It has a root over here and 2 more that are positive. And really, what we want to do is approximate these roots. And like I said, we don't have the tools for that yet. But now that we have some calculus skills, I do have this new tool to help us approximate roots of this function. And it's called Newton's method. Newton's method. And it is this super cool tool that uses some calculus in order to help us approximate roots of functions where we didn't have tools in order to approximate those roots or find those roots. So it's going to help us out a ton. And it's not just for this function here, it's for any real function. And just one other thing to say, you're getting a math introduction here, but you're going to see this probably in your introductory computer science class too, if you go take one of those and you're working with algorithms. So you're going to see Newton's method some more. But what is Newton's method? I've been talking about it and hyping it up. What is it? What does it do? And I think the best way to introduce it to you is to just show you graphically kind of what's going on with Newton's method. So let's say on this function here, we want to try to approximate this negative root here. Well, Newton's method says, all right, why don't you take a guess at an x value of what you think this root's going to be? So let's say our guess is kind of like right over here. And this is just a random guess. We'll call it x naught. And what Newton's method says, okay, now that you have your guess, make a tangent line for your function at this x value. So you come up here, and we know how to make a tangent line. Come up here, we make a tangent line. Okay, so this is x naught, y naught. All right, and then we make a tangent line here. So our tangent line looks something like this. Something like this. Okay, and let me get that in yellow. All right. Something like this. And now that we have this tangent line, what we need to do next is find the x-intercept of this tangent line. So that looks like it's right around here. And we can call this x1, that's our x-intercept. And you just keep doing this process. So this becomes our new x value, and then you make a tangent line for this function at this new x value, x1. So you come down here, we make another tangent line. Maybe it's somewhere over here. Let's make a tangent line. That's not perfect. Here, I'll try that one more time. All right. We're 0 for 2. Moment of truth. Here we go. Right there. All right. I like that one better. And we'll get that guy in green. All right, so there's our tangent line for x1 for this function, and then we can call this point, maybe we can call this point here, our x-intercept again we're going to find, and we can call that x2. So that's what Newton's method does. It makes a tangent line, finds the x-intercept, makes another tangent line under that x-intercept for the function, and then you just keep finding x-intercepts, making tangent lines, and eventually you approximate the root of this function. So that's pretty cool. And I've showed you graphically what's going on, and now I want to describe that generally. Throw some notation on what we just described over here. So we said first, we're going to make a tangent line for our function at this x value, x naught. We know how to do that, so let's draw that out. Y minus y naught is equal to f prime of x naught times x minus x naught. Okay, so this is a general tangent line here for our function at this point, x naught, y naught, and we can throw our function notation in. So we can say this is also x naught and f of x naught. That's also legal to say. So maybe we can fill some of that in. We have y minus f of x naught is equal to f prime of x naught times x minus x naught. And so this is our general tangent line. And we said what after this? After we made the tangent line, what did we want to find? Well, we wanted to find the x-intercept of it. So we wanted to find this x value, and we had to let y be equal to 0 to find the x-intercept. So we're going to let y be 0, and then we are going to solve for this x value. So we have negative f of x naught is equal to f prime of x naught, and then I'll distribute this guy right here. So we have times x minus f prime of x naught times x naught. And again, we want to solve for this x value. This x value here is really x1 in our graph. This is really x1. So let's solve for that x value and see what we get. I'm going to rearrange some things here. I'm going to get this f prime of x naught on this left-hand side and add this guy over. So after some rearranging, this is what we are going to get. We have f prime of x naught times x is equal to, and I'm adding this guy over, so I have f prime of x naught times x naught minus f of, not f prime, f of x naught, f of x naught. So that's what we get. Again, I rearranged things a little bit, but hopefully you can see that. And now, in order to find this x value, all we need to do is divide both sides by f prime of x naught. So we divide by f prime of x naught on both sides, and one more, f prime of x naught. And these guys will cancel, so will these. And we are left with what? We are left with x is equal to, we have an x naught minus f of x naught over f prime of x naught. And this x value on our graph over here, we could call that x1 if we'd like. We can call this x1 if we'd like. And this right here is what you would see for your formula for Newton's method in probably a textbook. But please don't remember this. Please don't try to memorize this. Just remember what it's saying. It's saying, okay, we took an initial guess at x naught, we made a tangent line for it, and we found the x-intercept. That's all it's saying. And Newton's method continues to iterate on this. So the next use of Newton's method is going to be this, under our example here. We're going to be finding x2, and that's going to be equal to, just using the formula that we got. This is x1 minus f of x1 over f prime of x1. Okay? And then if we want to use Newton's method again, let's say we want now x sub 3, and that is going to be equal to x sub 2 minus f of x sub 2 over f prime of x sub 2. And you just keep doing this, and eventually you approximate the root of this function here. And Newton's method is a powerful tool to approximate roots of functions. And again, you might be saying, okay, well, it's an approximation. How good of an approximation is it? And in the next video, we're going to see just how good of an approximation Newton's method gives in approximating the square root of 5.